Welcome to G Fun Facts Online. Ever wondered how your brain, that amazing 3-pound universe in your head, actually works? And what if we could take its blueprint to build super smart, super efficient artificial intelligence? Well, that's exactly what we're diving into today. We're on a journey from what scientists call connectomics, basically mapping the brain's intricate wiring to creating next-generation computation, or AI. It's a mind-bending fusion of neuroscience and AI, and it's promising to change everything. So buckle up. So what exactly is this connectomics? Imagine trying to draw a complete wiring diagram for the most complex city in the world, but instead of roads and cables, you're mapping every single connection between brain cells or neurons. That's connectomics. These connections, called synapses, form the circuits that control our thoughts, emotions, and everything we do. Scientists look at this at different zoom levels. There's the microscale, peering at individual neurons and their tiny connections, often using super powerful electron microscopes. Then there's mesoscale, looking at groups of neurons, and macroscale, mapping large brain regions using things like MRI scans. Now, get this. The human brain has around 80 to 100 billion neurons, and each one can make thousands of connections. Mapping even a tiny piece generates an insane amount of data. We're talking petabytes, which is like millions of gigabytes. But the progress is staggering. The very first complete connectome, for a tiny worm called C. elegans with just 302 neurons, took over a decade and was published way back in 1986. More recently, we've mapped the entire brain of a fruit fly. That's about 139,000 neurons and 55 million connections. And Google, working with Harvard, mapped a piece of human brain, smaller than half a grain of rice, in nanoscale detail. It had 57,000 cells, 150 million synapses, and took 1.4 petabytes of data to store. That's like a lot of high-definition movies, just for a speck of brain. Now, researchers are even working on the mouse hippocampus, which is structurally closer to ours. And here's a cool twist. AI itself is helping to speed up this massive mapping job, automating the tedious work of tracing neurons from these mountains of images. Okay, so we have these incredibly detailed maps of brain wiring, but a map is just a map, right? How does that help us build AI or understand how the brain actually thinks? That's where the computation part comes in. Scientists translate this structural data into computational models, essentially computer simulations that try to mimic the brain's activity and how it processes information. It's a multi-step process. First, get those high-res brain images and use AI to reconstruct the circuits. Then, represent these connections mathematically, often as a giant grid showing who's connected to whom. After that, they add details about the types of neurons, where they are, and what kinds of signals they send. Finally, they run simulations and check if the model's activity looks like what happens in a real living brain. There are even platforms like FlySim that can help build these brain-wide network models for simulation. Imagine having a personalized computer model of a brain. This allows researchers to do experiments on Melico, that means on the computer, like seeing what happens if a part of the network is virtually damaged, or how different therapies might work. So why go to all this trouble to copy the brain for AI? Current AI, especially the deep learning stuff that powers many things we use, is amazing, no doubt. But it often needs colossal amounts of data to learn and uses a ton of energy. Plus, it can struggle with things humans find easy, like learning continuously or using common sense in new situations. Now, consider your brain. It's doing incredibly complex stuff right now, and it's running on about 20 watts of power, less than a dim light bulb. Talk about energy efficiency. Building AI based on these brain blueprints could give us some serious advantages. Think AI systems that are way more energy efficient. This is called neuromorphic computing. Imagine AI that learns continuously and adapts, just like our brains do, thanks to something called neuroplasticity, where new connections form as we learn. Brain-inspired AI might also be more robust, better at generalizing from limited info, and less prone to getting confused by noisy data. And of course, the big dream is AI, with more human-like smarts in perception, memory, decision-making, maybe even creativity. Some researchers even think that by understanding the brain's reward systems, we could design AI that's inherently safer. This field is still young, but we're already seeing some super exciting results. For instance, scientists have used connectome data from the fruit fly's visual system to create AI simulations that can accurately predict how its brain cells will react to different images, without even needing to look inside a living fly for every experiment. This is huge for testing ideas about how brains work, super fast. Beyond the lab, combining AI and connectomics is giving us new insights into brain disorders, like Alzheimer's, Parkinson's, schizophrenia, and epilepsy. By spotting unusual connection patterns, we might develop better ways to diagnose these conditions and even create personalized treatments. Then there's neuromorphic computing I mentioned. Companies like IBM and Intel have already built special chips, like True North and Loihi, that mimic brain architecture. These chips are showing massive gains in energy efficiency for AI tasks, perfect for devices that aren't plugged into the wall, like in robotics or self-driving cars. And get this, personalized whole brain models, built from an individual patient's connectome, are being explored to help surgeons plan procedures, like simulating the effects of an operation before they even make an incision. Now, it's not all smooth sailing. Translating these brain maps into super smart AI is a massive challenge. First off, mapping the entire human brain down to every single synapse is still an unbelievably huge task. The complexity and the sheer volume of data are mind-boggling. And even if we have a perfect wiring diagram, that's just the structure. Figuring out how this physical wiring leads to dynamic brain functions, to thoughts, feelings, actions, isn't straightforward. There are so many other things at play, like different chemicals, gene activity, and the changing strength of connections, which current connectomes don't always capture. The amount of data generated is also a hurdle. We're talking exascale computing, that's super-duper computers, just to store, process, and simulate these brain networks. Biological brain cells are also way more complex than the artificial neurons in most AI models today. Trying to capture all that richness is tough. Plus, everyone's brain is a bit different. AI models need to account for this individual variability to be truly useful. And, ironically, the AI tools we use to analyze all this brain data might have their own limitations or biases, which could affect how we interpret these complex maps. But here's a really cool part. The relationship between connectomics and AI is a two-way street. They're helping each other out in a big way. AI, especially machine learning, is absolutely essential for speeding up connectomics. It automates the painstaking work of rebuilding neural circuits from microscope images, finding cells, and identifying those tiny connections. There are even AI tools like SmartEM that help electron microscopes focus on the important details, making the imaging process faster. So AI accelerates our ability to map the brain, and in return, connectomics is a huge source of inspiration for AI. Insights from how the brain is wired are fueling new AI designs, like those energy-efficient neuromorphic chips and new types of neural networks. Studying how brains learn, process information, and adapt is providing a goldmine of ideas for making AI smarter, more robust, and more efficient. So what's the long-term dream here? The ultimate goal of this connectomics to computation journey is to decode the fundamental secrets of biological intelligence and use that knowledge to engineer truly intelligent machines. Imagine future AI systems that are not only more powerful, but also incredibly energy efficient. Learn from just a few examples, adapt to new situations effortlessly, and have a much deeper understanding of the world. This could revolutionize medicine, giving us new ways to understand and treat brain disorders, leading to earlier diagnoses and personalized therapies. Think about advanced robots with brain-inspired AI that can interact with us more naturally and learn new skills much faster. Some even talk about whole brain emulation, basically creating a complete, functional simulation of a brain. That's still highly speculative and faces enormous hurdles, as a wiring diagram alone probably isn't enough. But beyond building smarter AI, the Connectome gives us an unprecedented window into our own minds, potentially helping us answer some of the biggest questions about consciousness, memory, and what it truly means to be human. This journey, from meticulously mapping the brain's connectome to building sophisticated AI models, is a monumental undertaking, but also an incredible opportunity. By tapping into the brain's elegant and efficient design, we're on the cusp of creating AI that's more powerful, adaptable, and maybe even more understandable. Of course, with such powerful technology comes great responsibility. We need to think carefully about ethical considerations like data privacy, especially with personalized brain data, the potential for misuse of advanced AI, and making sure these amazing benefits are shared fairly. Responsible innovation and open conversations are key. So the quest to understand and replicate intelligence is pushing new frontiers, shaping not just the future of technology, but our understanding of ourselves. What a fascinating time to be exploring the mysteries of the mind. Thanks for tuning in to G Fun Facts Online. What are your thoughts on brain-inspired AI? Let us know, and catch you next time for more amazing science.